Hi everyone, this is another part of the analog math series, and here I'm experimenting with differentiation and integration using analog circuitry. So first of all, what is differentiation and integration? Well, differentiation is essentially finding the rate of change of a variable with respect to another variable. And the circuits I'm going to demonstrate today um, only show the differentiation with respect to time, and also integration with respect to time. Integration is finding the area under the curve. Um, and the reason why it only works with respect to time is because uh, in the circuits that we analyze, we use the capacitor to create this sort of time component. And capacitors have a relationship that is defined by the current across them is equal to the capacitance times the change in voltage over change in time. Unfortunately, we cannot vary this change in time, so therefore the differentiation is only with respect to time, but we can vary the voltage across the capacitor, basically by setting the voltage at one end and then tying the other end at ground. So here we have the differentiation circuit. So let me show this circuit working first. So if I have the input as a triangular wave defined in my input node, triangle wave like this, um, I need to actually set the equivalent series resistance. And I'll tell you why in a second. But when I run the circuit, my output is a square wave. And this square wave, the value uh, is proportional to the slope, to the negative of the slope of the input. So for example, here, you can see that I have a positive slope, and this slope should be exactly at, let's see what it is. It's 0.5 seconds, 1 volt. So it's 1 over 0.5. So that's comes out to be at around uh, minus 0.04 volts. So the reason is because it's scaled, and I'll tell you why it's the equations now. So if we look at the equations, what's actually happening in the circuit is that the capacitor is generating a current that's proportional to the change in voltage over change in time, right? So C times capacitance times dV over dt. And so it's basically a voltage-driven current generator here. And this feedback circuit, what it's just doing is essentially measuring the current and converting it to voltage. And you can see that by the second equation, where the current going this way is equal to this node, the virtual ground across uh, the op amp, minus the output voltage divided by the feedback resistor, which is 10K here. And so if you equate the two equations, because the current can only go, can only go into the node from here and then out of the node into the feedback, uh, because op amps have, no current in their inputs. If you equate the two equations, you get the final voltage out is equal to the negative of the capacitance times the feedback resistor times the change in voltage over change in time. So do we actually have that here? Well, 1 microfarad times 10K is 0.01. And so uh, our voltage over time is 2 volts across 0.5 seconds. So therefore, it's 4 volts per second increasing. And then 4 times 0.01 is 0.04. And that's exactly what we see here, minus 0.04 volts. And likewise, when the voltage is decreasing, the um, the voltage jumps to the output voltage jumps to positive 0.02 volts. So it's measuring the slope, the inverse of the slope of this curve, and scaling it by minus C times RF. So technically, if we scale this up 100 times, let's just do that, 1000K. we should get, there you go, we get the output is 4 volts and minus 4 volts. Now, when you actually simulate this in LT-Spice, you have to put in a series resistance to the capacitor. If you don't do that, so I'll just show you, if I have no series resistance, you get these really strange oscillations. So why does this happen in LT-Spice? The reason is because if you analyze the equation of what happens across a capacitor, the current across it is change in voltage over change in time. However, the change in voltage in LT-Spice is not continuous because it's a computer simulation. What LT-Spice does, if you zoom in really hard into the input, right, let's zoom in right in, you can see that it's actually putting in a voltage increase with no time difference. So it's basically a straight line to approximate increase in voltage at the very micro level. And when the simulation runs, because the change in time is 0 volts, what happens is dV over dt is basically whatever this little difference is in voltage divided by 0. So it actually gives an infinite current whenever the voltage changes in the input. So that's why you get these sort of unstable states. And in real life, the reason why that doesn't happen is because, first of all, capacitors have a equivalent series resistance, right? Second of all, and because they have an equivalent series resistance, now you cannot have an infinite current across them. So there's an inherent current limiter in the series to the capacitor. Second is because the input source also has input impedance. So that's another, current limiting factor. And lastly, in real life, functions are not piecewise like this. So they're not basically nano jumps with no time difference. So that's why in real life you don't observe this sort of effect. And to combat this, all you got to do is just add a equivalent series resistance here. So I'm adding 1K so that it stabilizes faster. But if I rerun, you'll be able to see that the output is now again stable. Great, so that's differentiation. So next, let's look at how integration works. If you haven't seen my feedback, my op-amp feedback tutorial, basically how to inverse any function by putting it in the feedback path of an op-amp, I suggest you watch that first. But essentially, by putting the capacitor in the feedback path of an inverting amplifier config, we are inverting the current to voltage relationship through the op-amp. So what's happening is, again, watch that video if you haven't. But here, the capacitor is taking the output and differentiating it to get the current. So the voltage drop across here is basically a differentiating voltage and current relationship. So the op-amp basically tries to inverse that because it has to achieve Kirchhoff's voltage law. Like whatever happens across here has to happen the opposite way across the feedback. And so the feedback is differentiating, the op-amp basically integrates. And then this network just sets the current that the op-amp integrates with. So here, I've already, so here the equation is basically the inverse of this one, of the differentiating one. And it's, let me just type this out. It's basically V out is equal to minus 1 over RC times the integral of V in with respect to time. So this is that equation right here. And let's have a look at the output. So if you put everything here, so here I've got 100 microfarads and a 10K resistor. These two multiplied together become 1. So therefore, this is basically minus 1 times the integral of the input. So I have let me just demonstrate this. So I'm going to first use a sine wave to demonstrate it. So I'm inputting here a sine wave with a amplitude of 1 and a period of 1 second. So it's a frequency of 1 period per second. And my output looks like what you expect, which is a cosine. By the way, this is not actually minus 1, my bad, because it's actually, um, yeah, it is minus 1. The reason why the cosine is not negative is because the integral of a sine is negative of cosine. And it's got an offset. Obviously, when you integrate, there's an integration factor plus c, and c is the value of the cosine wave. You can find the c by getting the initial condition of the cosine wave. So obviously, the area under the curve is 0 at time equals 0. Cosine of 0 is 1. So therefore, the cosine needs to be shifted by minus 1. However, you can see that it's not correct, right? Because the height of the cosine wave, the amplitude is not 1 volt. It's like 0.16 volts. Why is that? Our calculations should indicate that the amplitude generated of the cosine wave, because the integral of sine is minus of cosine, should be 1. The reason why the amplitude is decreased like this is because sine, this is not actually sine of t. This is not sine of t. Sine of t has a period of pi seconds, of 2 pi seconds, my bad. And so this is much smaller than sine of t. So therefore, when we integrated it, there's a sine wt factor, and w gets divided after you integrate. And the larger the w, the smaller the output. So if we increase the period, we should actually see this sine wave increasing in magnitude until the period reaches 2 pi, in which case the the amplitude of the cosine becomes 1 volt. So let's try that. So we have our sine wave here, and if we increase the frequency to 1 over 2 pi, which is 1 over 6.28, we get, what is that approximately? Maybe 0.15 in terms of frequency. If we run that, you can see now our cosine wave is very close to 1 volt amplitude, right? So because 1 volt is here, the amplitude is very close to 1 volt. And it'll be exactly 1 volt when the frequency becomes 2 pi. Another thing to note is what's actually happening in the circuit. So like we know the mathematics works out, but what's actually happening is this circuit is feeding in a constant current, right? Because this end's tied at 0 volts. It's the input. Sorry, the input's not a constant current. It's a voltage-controlled current source here. So it's basically the voltage 2 divided by 100, 10K. So that's the current across here. And then the op amp is pulling this output, so increasing or decreasing the output to make sure that the capacitor, when it differentiates this output, creates this difference in current. So, the capacitor basically is pulling and pushing voltage over here, and it can only swing to the supply rails. So if it's too big, if the inputs are too big, what happens is it'll clip at one of the supplies. And something interesting I found on LT-Spice is that if the input is not does not start at 0, the integration circuit doesn't work. So, for example, I have a input here that starts at minus 1 volts, and the output is not the integral at all. The output actually slams straight to 100 volts, the supply rail. So why does it do that? Why is it slamming straight away to the supply rail? The reason is because, and I'll show you how to fix it. But the reason is because LT-Spice performs a steady state analysis. So uh, it tries to obtain the operating point at t equals 0. And it does that by um, basically replacing all inductors with a short circuit and all capacitors with an open circuit. And what happens here, right, is now this is an open circuit. So there's no feedback anymore. So again, this is another LT-Spice quirk, is that they try to simulate the circuit at t equals 0 by replacing capacitors with an open circuit, because they assume that at steady state the um, capacitor is an open circuit whenever there's a DC voltage being fed in. So if you didn't have a DC voltage, then LT-Spice will skip this sort of replacement, or at least maybe it also does this replacement, but it doesn't affect the circuit at all because voltage is 0, and then at t equals 1, the capacitor comes back, and everything's fine in the circuit. The way to solve this in LT-Spice, so if I actually wanted to integrate this function, is I could just skip the operating point solution, initial operating point solution. Skip initial operating point. The input and the output. So it works. The output now is the area on the negative of the area under the curve of the input. Let's check that. So we've got a triangle wave as the input. Let's check the area under this particular triangle. So it's 1 volt height and 0.5 0.25 volts width, and so therefore the area of a triangle 0.25 times 1 divided by 2 should be 0.125, and the height, which is the area, is 0.124 volts, so very close. And one interesting thing is, why is the integral of a triangle wave, why does it look like a sine wave? That's very strange. The reason is because lines are y equals mx plus c. So the x-axis is to the power of 1. And if you integrate that, you get something to the power of 2, right? And what this is actually not a sine wave. These are actually connected parabolas. They're connected parabolas with square power. So like y equals x to the power of 2's, like connected upside down to each other. So this parabola represents this one, represents this line, and then this one represents this line with an opposite slope. So I found that pretty interesting. Cool. So I just want to quickly talk about what's actually happening as well on the op-amp. So essentially, there's a current coming in through here, and the op-amp is pulling and pushing the voltage so that the capacitor, when it integrates this voltage change, can produce that current. That's essentially what's happening. And so that's integration. I wanted to create a circuit that can demonstrate integration itself in a useful way. So I decided to design this circuit, the power usage measurement. So I wanted to design a circuit that essentially can take in a black box component. So this is some component, we don't know what's inside it. And then we can set a power source of an unknown origin as well. So maybe this power source is a sine wave, is a triangle wave, whatever. And we only run the component for a certain amount of energy that it outputs. So let's say it's a fly swatter or something, and we feed in an AC voltage to that, and we only want the component to turn on after it dissipates like 1 joule of energy. So this is what this power measurement circuit is for. When you measure power in a reactive component, so a component with capacitors um, and inductors, which have reactance, you cannot just multiply the RMS voltage to current because they may not be in phase. Once you have reactance in a circuit, it can push the voltage and current across them out of phase, so that you can have a situation where every time the voltage is low, the current is high, and vice versa. And even if the RMS current and voltages are very high, the actual power output could be very low because of the phase difference. So in order to actually measure power in a black box like that, you either have to measure the phase difference, which is going to be almost impossible if your signals are not perfect sine waves. The other way to do it is you could just measure at every point in time the voltage and current across the component and then just sum them up. And that will give you the energy output. Um, because you'll be able to capture those phase differences. So here, this is what the circuit is doing. This LCR, this capacitor inductor um, resistor series is the black box. We can basically model an unknown component to always be some sort of a combination of this. And this is the power source. It's basically inputting a sine wave. And I am taking the voltage across the component with respect to ground and the current across it by taking the current with respect to a shunt resistor that I put in series with the component. And this shunt resistor is 1 ohm, so it doesn't really change the voltage at all. And it doesn't impede the current very much, but we just can use it to measure the current. Because current across the component is going to be current across the shunt resistor, which is voltage across the shunt resistor divided by 1. So the voltage here is actually the current across the component. And then we use a Gilbert cell to do the multiplication. We multiply the voltage across component with the current across component. And this is basically done at any point in time. And we then put it through an integrator to integrate it with respect to time, right? So this basically gives us the area under the power curve. And when we sum up the area, that gives us the energy. This is just an inverter and scalars to scale the value back up to appropriate power value. And the power calculation that I've set for this circuit is the voltage output here, output on this line, indicates how many millijoules of energy has been outputted. So then there's a comparator here that compares this energy output to a set value. So here I've used the voltage divider to do that, and I've set it to 20 millijoules, essentially. And you can do this with a much better thing than a voltage divider. You can use a potentiometer here to adjust it, or even a straight signal from an Arduino or something like that. And so this comparator will basically pull high and low, basically this NMOS MOSFET, to allow the current to flow or not flow. So essentially, after 20 millijoules of current of energy has been dissipated by the circuit, it turns off the circuit because the gate is going to be pulled to ground. So if we look at the actual energy output, you can see that the gate remains at 20 volts for the whole 5 seconds. So it never reached the 20 millijoule threshold. So why is that? Well, theoretically, the power output across the component is the highest during the resonance frequency, when the signal was coming at a resonance frequency. If the signal was too low, like if the frequency of the signal is too low, which means it's too close to a DC signal, the capacitor will block it. So therefore, the current will be small. And if it's too high, so if the frequency is very, very high, the inductor will block it. So therefore, the current will be very low again. So therefore, there's not going to be that much power dissipation across the resistor, because the resistor is the only component that actually burns the power. The inductor and capacitor does not emit power; they store and release power back into the circuit. The time when the power dissipation is the highest is during resonance, where the capacitor and inductor basically cancel each other out and have the highest possible current through the resistor. And that's determined by this equation, 1 over 2 pi root LC, which for the circuit is 516 hertz. So at 2K, we see that the power dissipation is really low, so it never hits the threshold. And then if we look at 1K, let's run that. There you go. So it hits the threshold and we turn off the circuit. And it hits the threshold at 4.47 seconds. So what if we put in the resonance? Theoretically, this should actually shut off faster than 4.47. So if we put that in and run, there you go. So it is faster. It's a little bit faster. It's 4.3 instead of 4.47. And if it's too low, let's put it at 100. So this is closer to a DC. So we should expect, there you go. So it never reaches the power dissipation required to emit 20 millijoules. And yeah, this is a power measurement circuit. And when I was designing this, I was actually a little bit surprised that something like this can work because, if we integrate the power over time across something like a resistor with a sinusoidal voltage input, isn't that going to be zero? Because the voltage swings from positive to negative, and so does the current. But actually, no. The integral of the power over time for just a resistor is always positive because the voltage is always in phase with the current. So you got a positive times positive or a negative times negative, which equals to a positive sum. So the only time when it could be out of phase is when there are reactive components. And if it swings negative like that, it's basically the reactive components dumping energy back into the circuit. So when you sum it all back out again, it actually does equal the true power dissipation, which is very surprising to me. But yeah, the mathematics works, and it does make intuitive sense after you think about it for a while. All right, that's it for the video. Thank you very much.